Okay. So let's this unit 3.4. It says rate of change and the natural social sciences. Well, natural. Is there anybody else who hasn't gotten notes yet? Anybody else? There you go. My cord doesn't reach that far. Okay. So today we want to look at an application to a moving object, in particular a particle. So this is stuff you have to memorize. Okay. Don't know. It's extremely important that in this unit you keep in mind what the position function is, the velocity function, and what those pieces mean. So position function means where you're at a given time. The position function does not tell you how fast you're moving. It does not tell you how many cumulative miles you've traveled. It simply tells you where you are at a given point. The velocity function. How do you measure velocity? Sure, you could say meters per second. So the velocity function is this. I noticed that I always give myself a haircut lately, and I wasn't able to really get the back. So I tried on my own, and it didn't work. So my wife kind of tried to clean it up a little bit. So, yep, yeah, but the back is hard to do. You have to, it doesn't work like that. S prime. The velocity function is equal to the derivative of the position function. So if you want to know how fast you're traveling at a given time, that's what we have to find. So particle is at rest. If the particle is at rest, what is the velocity? 0. Particle moving in the positive direction. If the particle is moving in the positive direction, what is going to be the velocity? The velocity will be positive. What if the particle is moving in the negative direction? So, let's give this a shot. It says, example 1, a particle is moving according to the law of motion S equals F of t for t greater than or equal to 0, where t is measured in seconds and S is in feet. Okay? This is our function. It tells us where we're at a given time. Okay? First of all, I just want you guys to have this understanding. Where am I currently at time 0? Where's my position at time 0? 0. If you plug in 0, you get 0. You don't necessarily always start at 0. You might start at something else. If there's a constant on the end here, then you don't start at 0. You have to keep that in mind. Find the velocity at time t. How does the velocity function relate to the position function? derivative. So v of t is the same as s prime of t. Okay? What is the derivative of that function? 3t squared minus 12. Okay? Very good. What is the velocity after 3 seconds? How would I find the velocity after 3 seconds? Plug in 3. So v of 3 is equal to 3 times 3 squared minus 12. 9 times 3 is 27, minus 12 is 15. Now, it says that we are measuring time in seconds and we are measuring s in feet. You must put a label with your derivative. Feet per second. When is the particle at rest? How do I find that? Look at our notes. We say that we take the derivative and set it equal to 0. So the velocity function, we take it and set it equal to 0. So we have 0 equals 3t squared minus 12. Does that factor? Yes. 0 equals 3 times t squared minus 4. T squared minus 4 factor? So, what are my solutions? I want you guys to think of this for a second. Do you have negative time? No. It says, even at the beginning, for t greater than or equal to 0. That restricts our domain to be only non-negative values. Excuse me, we can include 0. So non-negative values. So we discard the negative 2. But rather, the particle is at rest at time equal to 2 seconds. When is the particle moving in the positive direction? You have your derivative set greater than or equal to 0. Now, I'm going to put a challenge to you guys. I think most of you don't know how to solve this problem. I think most of you, when you get to this problem, you immediately want to factor it. You want to take both pieces instead of greater or equal to 0. Well, even if you add the 12, that's not the way we do it. You can only solve linear inequalities by doing the method that you're talking about. If you remember for pre-calculus, you have two methods for solving non-linear inequalities. Number one, you can set up a box with a bunch of plus or minus values, or you can look at the graph. Okay, we have those two options. Okay, all right. So, yep. So here's what I want to do. Okay. I want to help you guys understand graphically what's going on. Again, if you really want to be a refined mathematician, you got to be able to think about the graph as well as the algebra. So we have v of t down below. We're going to have s of t up top. And let's just think of this graph. What does t to the third minus 12t look like? That's a kind of that cubic looking function, kind of like an s, right? In fact, if you wanted to, you could find exactly what the function looks like by going s of t is equal to t times t squared minus 12. So you know that the function crosses through what? 0, and if you solve this, you would get positive or negative square root of 12, right? So this graph, and the positive negative square root of 12 is about 3.5, negative 3.5, right in there. So I'm just going to give you an idea. This graph looks approximately like this. That's approximately what that graph looks like, the position function. Now, again, I have my t-axis and my s of t-axis. Can t be negative? No. So I want to erase, in order to graph this function correctly, I have to restrict the domain to only be positive values. I'm sorry, non-negative values, because we can include 0. So that's what this graph looks like. Now, let's think about this, everybody. Right off the bat, am I headed in the positive direction or the negative direction? How do you know? Because the slope's negative. So let me jump over here. Am I heading in the positive direction or the negative direction? Positive. Even though I'm still below the x-axis, the position which I'm traveling, I'm still at a negative mark. I'm going in the positive direction because the slope is positive. Well, we want to graph the derivative down here, and it should match with that. We should have a 0 right at about 2. Let's look at this graph. You guys told me that this graph, this looks like a parabola, does it not? Shifted down how many units? 12? Y-intercept is negative 12. So it starts all the way down here, okay? And it crosses the x-axis at what two values? Positive 2 and negative 2. So if you look at this parabola, it looks something like that. Now, can we have negative time? No, so we can get rid of that back part of it, but that's what the graph looks like. Sure. So it says, when is the particle moving in the positive direction? You tell me, okay? When the particle is moving in the positive direction is when the derivative is greater than or equal to, or when it's greater than 0, okay? Is the derivative positive here? This is the derivative. Is it positive? It is negative. Look, this is the derivative right here. I am below the x-axis. I am negative. If I move back up here, that corresponds to this part where you're going down. The part where you're going down corresponds to the part here where you're below the x-axis. That's how those graphs are related. So, again, is the derivative positive or negative here? Negative. Is the derivative positive or negative here? Positive. So, everywhere from 2 and on. So it says, when is the particle moving in the positive direction? Time greater than 2. At equal to 2 where the particle is at rest. Find the total distance it's traveled during the first 8 seconds. Watch. Here's what we got to do. We first figure out where did I start. If I want to figure out where I start, do I plug that into the position function or the velocity function? The position function. That tells me where I'm at. So where am I at time 0? 0. So the particle starts at 0. Now, will the particle begin by traveling to the left or to the right? Why does it begin by traveling to the left? Because the derivative is negative right away. Exactly. There's 2 graphs that show you the derivative is negative. If you look at this right here, you can tell the derivative is negative. If you look at this part right here, you can tell the derivative is negative. So I'm heading in that direction. Okay? So I'm going to start right here. Here's Mr. Particle, and it heads off in that direction. Okay? Now, when does the particle stop moving in the direction to the left? At time 2. If I want to figure out where I am at time 2, do I plug that into the position function or the velocity function? Position function tells me where I am. So even though we got that value 2 from the velocity function, we plug it back into the position to figure out where I am. If we plug in 2, you get 2 to the third, which is 8 minus 24, negative 16. So the particle starts here, and it travels all the way back to negative 16. I'm just going to make a note here. That's at time equal to 2. This is at time equal to 0. When I hit negative 16, what happens to the direction of the particle? It starts to turn back around and head to the right. How do you know that? Because the slope becomes positive. Look at my graph. Negative. The derivative is negative. It's traveling to the left, to the left, to the left, to the left. It stops at 2, and then travels to the right, to the right, to the right, to the right. Yes, it will travel to the right forever. Okay? Now, I'm trying to figure out the total distance traveled during the first 8 seconds. Does it change direction again after 2 seconds? No. So I want to figure out where my position is at time 8. So what would we plug it into to figure out where my position is at time 8? The position function. So let's plug it in here. What is 8 to the third? 512. Minus, here, let's just plug it in. The calculator isn't going to turn on. 496, sounds good. So if we plug in 8, we get 496. So that means the particle travels all the way around, and at time 8, it's at a position of 496. So I want to figure out the total distance, it says. So I drew the diagram in order to illustrate the motion. That's what it's done. Okay. Now what I want to do is I want to figure out the total distance. And the way that I do this is I try to make it as least complicated as possible. I always draw a line right at the start, right at 0. How far did I travel to go from here to here? 16. How far did I travel to go from here to here? 16, and then how about here? 496. So we have 496 plus 16. Oh, it's 416. So if we take 416 and add 32 onto that, we get so my distance is 448 feet. I traveled 16 feet to go back, 16 feet to get back to 0, and then 416 feet after that. Shh. Let's review, everybody. Okay, real quick. How do you find the velocity? What do? You take the derivative, okay? In order to find out what the velocity was at 3 seconds, we plugged in 3. In order to figure out where the particle is at rest, you take which function? The derivative function, or the velocity function, set it equal to 0. When is the particle moving in the positive direction? You have to look at the graph and see where it's above the x-axis. Find the total distance. You have to find your starting point and the points where you change direction. Do you plug your times into velocity or into the position function? The position function. Now, we've got a couple more examples like this, but I want you guys to practice a couple basic problems like this right away. Super important that you wrap your brain around this because we come back to this in a couple weeks again. For any YouTube watchers, there's the assignment. I just wrote what 5 and 6 were because 5 requires use of the quotient rule, 6 requires the use of the product rule, or you could distribute this through and then just use the power rule. That's up to you. But that's what we're going to pick up with tomorrow. Try those problems.